I welcome back all the participants for session 3 of Day 1 FDP on integration of renewable energy and smart grids for smart cities. I now take the privilege to introduce the speaker for the session, Dr. Senthilarasu Sundaram sir, Senior Lecturer in Renewable Energy, Environmental and Sustainability Institute, University of Exeter, Penryn Campus, Cornwall, United Kingdom. He got his MSc degree in physics in 1999 from Bharatiya University, Coimbatore, India. His MPhil in Applied Physics in 2001 from PSG College of Technology, Coimbatore. He got his doctoral degree in 2006 from Bharatiya University, Coimbatore, India. He also acquired postgraduate certification in academic practices in 2014 from University of Exeter, UK. His research interests include energy technology solutions towards depriving community needs and aiming to address critical energy issues to benefit the society. He is a solar energy material and system scientist with 18 years of research experience. He is expert in thin film photovoltaics, Dyson-state solar cells, room temperature perovskite thin film solar cells, and its building integrated applications and concentrated photovoltaic applications. He also got his expertise in scale-up engineering of the lab-scale devices to system-level modification. He has 127 journal article publications with total 3,700 citation and H-index 30. He secured a total funding of £10 million as PI and co-PI with currently 7 ongoing projects. He has a contribution to Research Excellence Framework with publications of impact factor 12. He is carrying a 4-star impact case studies in GCRF themes. I would now request Dr. Senthilarasu Sundaram sir to hand over the session. Sir, please.
Thank you very much. Thank you very much for your kind introduction. I'm sure you can hear me and see me as well.
Yes, sir. Yes, sir.
Thank you. So I first of all, good afternoon to everyone who is attending from India, and then good morning to the people who are attending from Europe or some other places. First of all, I just wanted to give a brief introduction about me, even though she has introduced me very well. And so, as she introduced, I graduated from Bharatiya University in 2006. And then after that, I worked in Chonbuk National University in South Korea for a couple of years. After that, I worked in National University of Singapore, NUS, for 1 year. And then I moved to UK in 2009, actually. So that's the long journey. Ends in Exeter by 2013. I started as a lecturer here, and then I'm a senior lecturer in the renewable energy um, um, last maybe 4 years now. Yeah, so that's the brief introduction about me as a person, who I am and what I'm doing. And what I'm doing as a researcher, or the as a group, what we are trying to establish in our lab here, I try to give you a kind of a overview about myself and my group, what we are doing, and then I will explain you some of the works what we are doing here. So my research group name is actually Solar Energy Materials Group. So in that one, we try to establish materials, and then trying to make devices which is in the laboratory scale, very small devices, as most of you aware of it. And then we try to scaling them up into a bigger, the day-to-day life activities, like the commercial activities, what the companies can do, and how they can scale them up, and what type of challenges they will have, how they can overcome it, and how this can be established in different types of applications. So that's what I'm doing. Most of my work is based on the third generation type solar cells, or the new types of solar cells. And in those type of solar cells, particularly, I will be working on the thin film type solar cells. cadmium telluride, copper indium gallium selenide, these type of materials, as well as dye-sensitized solar cells. And last 4 or 5 years, I'm working in the perovskite type solar cells as well. So if you are asking me, so is that the only thing I will be working, only the device from the photovoltaic perspective? Certainly not. I will try to work on the thermal side of the solar photovoltaics as well. So I'm trying to store that energy through different types of materials, and then using them for different types of applications. We will be just putting them those materials like wastewater treatment, agri-tech types, and then some of the innovation also will be doing actually. Um, in terms of a group, as a solar energy group, we focus quite large variation of the things. So the first one, most of our devices and materials, we try to see whether they can be applied in the building integration. So not only as a rooftop, so if you're putting them as a glass, like a windows or a shield, or like a shades, so what type of effects they can give, and how to tweak them to find the balance between the light and electricity generation. So how much light can be come inside the building, and how much energy I can able to make. So that's the kind of area we work largely, like 70-75%. And then about other 20-25%, so we try to focus on various types of ones, like an electrical vehicles. So especially integrate our solar panels into the cars, and then some other vehicles as well, especially on the solar boat. So if you take the solar boating, throughout the world, we try to use quite large amount of vehicles inside the sea. Most of them are using the fossil fuel and throwing quite large amount of waste into the sea, and then it's affecting the marine life and other stuff. We try to fix some of these issues by having a solar boats. What we generated here, so we generated a speedboat, so which one can sit and then just do couple of miles running towards that one. So that's like a research element. So from that research element, we try to establish the bigger type boats as well. You may think it's not very new. So what you are doing as a new kind of a technology development in your lab. So as you rightly guessed, it's not new actually. But what we try to establish, there are lots of other elements to fix them to get the energy efficiency higher. So that's what we try to focus on, these type of activities as well. And then most of you know about the Tesla roofs. So the Tesla roof is nothing but the company Tesla. So they try to integrate the thin film solar cells onto your roofs, like slides or like a tiles, and then generating the electricity to charge their cars actually. So that type of activities also we try to do, but not exactly what Tesla will be doing, but we try to establish some of the other materials as well. And then the one you will be seeing here, so this is called Solar Square, so which one of our teammates, Dr. Hassan actually, so he has made this Solar Square, and they spinned off a company which is called Build Solar, and they trying to develop the concentrated type of photovoltaics as well. Then I put this one, the sun here. This is the photo which I have taken in Hyderabad actually. So we try to maximize the energy from the sun. So whatever the solar materials what we have, either they can particularly absorb particular portion of the light, not the entire portion of the light actually. So we try to have an different ways of approaching the solar cells to have a complete absorption of the solar energy. And apart from these ones, like, and these are all kind of the advanced technologies, are people who really just putting their life into a sophisticated mode, then they can try to have these ones. But day-to-day life, the lots of farmers, they're struggling with the electricity what we are providing. Most of the countries actually, not only in UK, and Africa and developing countries like India, so they're all struggling for the electricity. So how these can be, the solar can be integrated with the agri-tech products, and then how we can able to give them a kind of sophisticated environment for them to use the solar. That's also one of our focuses actually. And then last 2-3 years, we try to focus on the water desalination, and then water sanitation, and then water remediation as well actually. So these are all the large amount of work we will be trying to establish. As she mentioned in her introduction, so GCRF means the Global Challenge Research Fund. So meaning that, so some of the challenges we face throughout the world actually, like water, electricity, and then clean air. So these are all the biggest problems we have for this century actually, even though our pandemic is affecting the total world. So apart from that pandemic, there are lots of other things we need to give our concerns, or we try to focus on these ones also. As a group, we try to establish these areas, and I'll be explaining you some of the research what we are doing here. And before going into that research, um, I'm sure most of you have seen this chart in different types of different talks or different presentations and other stuff. So I will try to give you a different perspective for this chart actually. So this is the chart which will be available in the NREL, so National Renewable Energy Laboratories from US. So they will be making this photovoltaics efficiency chart every 6 months once actually. So in this one, so whatever you are seeing in here, so they are from the different types of solar cells. So the solar cells is not only made from the silicon, so we have quite large amount of materials like thin films, like emerging PVs, like dye-sensitized, perovskite, organic materials, and then inorganic materials. So there are lots of other kind of device variations like single junctions, double junction, triple junction. So those type of cells, and then ordinary light conditions, concentrated light conditions. So these are all there actually. But if you want to take them into a market, or into the people who are using them day-to-day life, so you need to have certain kind of standards to get that standard. So you need to know the efficiency of the system. The efficiency of a solar cell is nothing but if you are throwing 100 photons onto your solar panel, so maybe out of 100 photons, so you can able to take only 20 photons as electricity outside of that device actually. So that the 80 will be converted into a heat or doing something else to the solar cells, and then the 20 percentage of your photons can be utilized as a electricity sources. So that's what we are mostly interested throughout the world. So this chart will give you a compact figures of what type of materials, and then what will be the record efficiency in the laboratory scale, not in the commercial scale actually. So if you are seeing these ones, it's vary from 12.6 up to 47.1 or 47.3 nowadays actually. So this is the maximum efficiency you can achieve with the current technologies what you have from the solar the world. So what I'm working partially on this side, and then partially on this side actually. So some of these ones are kind of the babies you will get. So when you are growing it up, so you don't know what type of man you are going to get, right? So those type of activities also we try to do actually. So I'll explain you in the slides. Before going into those details, I want to give you another kind of a perspective to the solar world, or the PV world. So so the solar technology started in 1954. So it comes from the silicon. So the silicon is one of the very bad material to absorb the sunlight and then convert them into electricity. I don't know how many of you know about it actually. So if you take the physics of the solar cells, the silicon is one of the worst material to use as a solar cell actually. So this one we call them as the first generation type solar cells. So because in 1954 the transistors were booming, and then everybody was using the silicon chips to make the transistors. So those type of transistors actually, so they accumulated a huge amount of waste. These electronic companies, they don't want to throw the waste, and they wanted to use them or recycle them in a different way. So that's how the solar industry, they get the holy grail material like the silicon, and trying to prepare their solar panel from there actually. Right. So in 1954, the first solar cell was created by the Bell Laboratories in US. So they got about 5 to 6% efficiency. And then after some years, like up to 70, 75, so they are using these as a technology, but nobody believed. So this is going to change the world in 2000 or 2020. So they don't want to invest quite a lot of money into it actually. But if you take the advantage of this one, it's up to now, it's about 70 years of old, these technologies actually. So they are very mature technology and very high efficiencies you can able to get. The disadvantage side of these ones are very costly, and then large material usage you need to use. So that triggered the second generation type solar cells. So the people don't want to use large amount of materials to absorb the light and then convert them into electricity. So they want to have reduce the material usage. So that's how thin film evolved as a second generation. So there they significantly reduce the thickness of the devices, and then they go from 400 to 500 micrometer thick devices to few micron, like 1 micron or 2 micron like devices. So when you are reducing the thickness, you save huge amount of materials as well. So that becomes an advantage for this one. So as a less material usage and then high efficiency. But the downside of these materials are, so they are like they just follow the technology what the first generation was using actually. So that's the another kind of the investment and everything is almost the same like the silicon, right? But the other kind of advantage to the thin film is not using the indirect material like the silicon. So they try to use the direct materials like CAGS and cadmium telluride and other type of gallium arsenide type materials as well. That created the kind of the innovation in that field. But still people are worrying about the highly energy intensive processes which is going through the silicon and thin film, and then the amount of toxicity they created is huge. So that triggered the third generation type solar cells, which is the you can able to get the higher efficiency, and then environmental friendly materials, as well as the low the disadvantage is the low scalability, and then they have a huge amount of scaling up challenges to tackle. So these anyway, we are going to talk about the third generation PV for another 40 minutes also. So I'll explain one by one hereafter actually. Right. So these are all the basic differences between the first generation, second, and third generation type solar cells. And the main difference between the silicon and the third generation or the second generation solar cells is here. So if you're taking a any type of silicon, single crystalline silicon, polycrystalline, whatever it is actually. So the thickness you need to have, the minimum has to be 200 micrometers. The maximum, sometimes it can go up to 400 to 450 micrometers of the thick actually. So the thickness of the layer. The area of the devices will be defined by the wafer sizes. If you are having the maximum size you will get is about 15.7 by 15.7. So that's the device area you can able to get from that one. And so they are made up of the silicon bases. So they are very rigid actually. So they are very brittle and rigid as well. And then the module integration will be very, very complex in the silicon type ones. The thin films are they are not depending on the only one type of a material. So, but you have varieties of materials actually, including perovskite actually. So I'll explain you so why I put the perovskite here as a thin film, not as a third generation type material. So the thickness of these ones, so the minimum you need to have at least 2.5 micrometer, and then maximum you can go up to 10 micrometer. So you can compare from 200 micrometer to 2 micrometer. So how much the materials you are going to save. And then unlike the wafers, so you will have a deposition. The large area deposition can give you a large devices like a meter by meter devices also possible. And then because these materials are not comes from the rigid background or rigid type of substrates, you can able to use any type of a substrates like a flexible substrates like a polythene substrates or like the metal substrates. So something like that you can use. And then the interconnection between these cells are the monolithically connected. So they are not like so you will have a device and you need to connect the positive to the positive, negative to the negative. So that will not, so that complexity will be reduced from these type of monolithic configurations. So why I'm particularly very much interested. So, I don't want to see the very dumb buildings with the gray color, black color kind of a things. So if you have a window, so you need to have a very colorful one. So what will be the option you can have? So the third generation solar cells can offer you a very colorful type of windows, shades, and other stuffs actually. So then you can able to tune the band gap, and then you can able to get the desired color. So as far as I know, so about 255 shades you can able to make. So you have more than 3,000 or 2,500 organic molecules are there to make these type of colors as well. And then what is third generation solar cell? Okay, so the third generation solar cell, you can put three major elements. So one is the dye sensitive solar cells. That classically it started in 1990s, I guess, actually. So then it started by Gradesell, Professor Gradesell, Michael Gradesell. And then so when he started working on it, actually, so mostly he will be trying to put the layers and then put some of the electrolytes inside. So you'll have basically the liquid based junction. So to avoid the liquids inside the solar cells, and people try to achieve the organic type solar cells, and exactly like a thin film solar cell. So you have a p-type material and n-type material, having them join them together and trying to get the more energy conversion from that one. So the advantage of these materials, unlike the first two generations, so these materials are very flexible. You can able to cover the entire solar spectrum by tuning the band gap, or by having a different types of materials, something like that. So so once you have lots of difficulties with the dye sensitive solar cells, as I explained you about the liquid junction, and then you have organic materials inside, so they degrade over the time period, and then that is the hindrance for the efficiency. So what you are getting, so mostly you will get like 14-15% in the laboratory scale, and in a industrial scale you will get like 10 or 11% efficiency of these materials. So when people are trying to so make different types of combinations and other stuff, so the perovskite solar cell comes as a savior to save everybody actually. So you try to use some of the perovskite materials as a electrolyte in the first place, and they got a very good breakthrough in that one, and then they got a very good efficiency. So we'll come to that one later. So in these ones, so why I'm particularly interested in, they are very flexible. You can able to make in any type of substrates, and then you can able to put in a different types of climatic conditions as well, and you can able to create the entire spectrum absorption materials actually from that one. Then they are very colorful as well. And so these are some of the the aspects, and then the commercial aspect to them are they are very low cost ones. So you can able to make them in the low energy production cost overall actually. So if you take, and then they are mostly using the environmental friendly ones. So we'll say like, and so mostly they are using environmental friendly materials. Not all of them are environmental friendly. Okay, so the challenges for these type of materials are three different areas I can see. The efficiency of the devices. So if you take dye-sensitive solar cells, so they are trying to give you like 14% maximum, as I said. The organic photovoltaics, maybe they can give more than 10% efficiencies. But for the perovskite materials, you can get about 25% of the efficiency. The efficiency mostly fixed for these type of materials, fixed in the sense, so they are very high efficient materials. You can able to get them, so going for the commercial scale activities as well. So but the scaling up will be a big issue for these type of materials. So for example, dye-sensitive solar cells, so somewhat you can get like the bigger kind of modules, about 10% efficiency. And then organic solar cells, they are very well proved ones, so they can able to get like more than 13% efficiency in the commercial scale ones. And for the perovskite materials also, they can able to get the maximum about 17-18% in the module level nowadays actually, right? So these two can be fixed. So the efficiency of these systems can be fixed, and then the scaling up challenges can be fixed, and then one way or the other you can able to fix. But the stability and reliability of these materials will be a big question mark. So if you are taking some of the dye-sensitive solar cells, their lifetime will be 5 years or 6 years, and then less than 10 years actually, you can say. Most of these three devices will give you a lifetime of 10 years. So if you take one side thin film solar cells and silicon, they can offer you 25 years of efficiency warranty, or the conversion warranty. So that cannot be matched by these type of solar cells. If I'm a building owner, if I wanted to put a solar window in my window, so I will not prefer these devices, even though they are very colorful. So they are environmentally friendly made, but so I need to change my window in 10 years time. So I'm not going to be doing that actually. So that will be a biggest challenge for me as a building engineer or building owner actually. So in that case, so I will try to adopt the established technology in there actually. So this is the biggest challenge for third generation type solar cells. And some places people are trying to overcome these ones as a research side, and in the commercial side it's a big question. So what we are trying to establish actually, so in terms of energy conversion, so we use quite large amount of materials. So we use TiO2, we use tungsten oxide, we use the perovskite materials, not only the one you'll be seeing in the most of the papers. So we use quite large amount of other type of perovskite as well. And we mix them together and we try to create the materials not only for the efficiency and solar panels, and trying to have rectify some of these issues like the dust accumulation issues, and then building integrated issues, and it can be used for the agri-tech products as well. So nowadays, last 3-4 years, we use quite large amount of carbon based materials like reduced graphene oxide, graphene, something like that actually. So most of my presentation will be based on the perovskite type cells, and give you a kind of overview about these type of solar cells. And so these are all the kind of the history happened maybe 10 years ago. So I'm fortunate to work with some of these people like Henry Smythe. I worked in the sense, so we were in the one forum. So we try to work together actually in some of the dye sensitized solar cells as well actually. So this is the dye sensitized solar cell, and which is having some of the liquid electrolyte inside. And when you are changing this one with the spirometate and then having some of the perovskite materials inside on top of the TiO2, so you will get the clear kind of a perovskite solar cells actually. So this is the one for the DSSC, and then the liquids are not the desired materials to use within the solar cells. Then people trying to use the solid state devices. For the solid state devices, they have used huge amount of variations of the materials, and from the gels to semi-liquids and some of the whole transport materials and other stuff. The spirometate is the one which was used for the solid state dye-sensitive solar cells. And then extremely thin absorbent layer materials are trying to reduce the dye usage here, and trying to have some of the other type of dyes, so as a extremely thin absorber layers on top of the TiO2, and try to achieve the extremely thin absorber layer devices actually. And the efficiency of these ones, except dye-sensitive solar cells, these two are extremely low efficiency, like a 5%, 6% efficiency, and then ETA will be giving you like 6 or 7% efficiency. So from that one, so they try to replace the extremely thin absorber layer with a perovskite material that gives you the boom, like from 3% efficiency to 10% efficiency. These are different types of architectures. So people are trying to use over the time period, like PIN junction, PN junction type devices, which widely used in the thin film industry as well. So it started like 3% efficiency, and then it achieved like 25.2% or 25.5% nowadays. So very quickly, just like that actually. So like if you take any type of solar cells, like a silicon will take like 70 years to achieve 25% efficiency, but thin film like a Usain Bolt, so it just achieved like that. Okay, so then the growth of the PSC, it take like so whatever the silicon take 50 years, so they have achieved like in 10 years time actually. So like just boom. So there is an advantage for it. There is a disadvantage of this one also. The disadvantage is every 1 hour there is an article published for the perovskite or by the perovskite community. So finding the niche to work on, or finding the correct type of research ideas or research themes to work on will be extremely difficult to work with the perovskite ones. Perovskite materials are not the new materials which is just came 10 years ago. So they are comes from the long background, like a 200 years old materials. So like a calcium carbonate, calcium titanate, so strontium titanate. These are all the perovskite materials. So the perovskite is nothing but actually so you will have some of the materials will be in here, and you will have rest of the ions will be on the tetragonal shape actually. So what we try to establish in our lab, we try to establish the stability and longevity of the devices, and we try to have the flexible and scalable techniques to use, and then we try to use some of the innovations within the solar cells as well. So in terms of stability and longevity, most of the highly efficient devices from perovskite are made from a glow box environment, or the controlled atmospheric conditions. What we try to establish is we try to establish in the room temperature based perovskite ones. So our efficiency levels are nowadays like 15 to 17% efficiency we will be getting, and then we get the longevity about 3 months, 4 months. So the efficiency will not drop down, or maybe dropping down maybe 10 to 20% of the one. And we try to use the screen printing technology mostly, and we are trying to innovate our coating technologies by the 3D printing or the inkjet printing type materials as well. We use quite large amount of graphene as a whole transport material, and then we try to establish some of the concentrated aspects to our solar cells as well. So some of the results I try to share with you. So we have used some of the techniques, like the very old techniques, like tuning the band gap, or the tuning the morphology of the material, and by tuning them you will get the very good kind of a efficiency increase, as well as you can try to maintain the efficiency for a longer time. So when you are tuning the morphology, so what you will get, if you are getting a 3% or 2% efficiency, so after the initial reduction from 1 or 2 days, if exactly speaking, after 2.5 days, so it will try to just keep the efficiency going. So these devices are not um, laminated devices. They are the bad devices. You just make it and then keep it outside, and then trying to see what type of an stability they are trying to create actually. So by using the different types of morphological stuffs, so we try to establish what type of an relationship you will have when you have the morphology difference in your solar cells. And this paper published in the materials letter, it's available. You can go and see, or if anybody wants more information, feel free to ask me as well. So and then the from the morphology tuning, so we try to increase the efficiency also. So when you are trying to use different types of environment, and then temperature controls, how we can able to establish these type of stability, as well as the longevity of these devices. We do quite large amount of modifications. So one of them are so trying to have different treatment timings with sodium hydroxide and then the citric oxide, with the different types of variations, and then we try to treat the materials with the different types of temperatures as well actually. So they are not the classical type perovskites. So we try to establish the different types of perovskite materials to use actually, even though their efficiency are low, but the stability will be very good actually. So our idea is to use these type materials in the classical type perovskite materials, and then trying to see what type of efficiency we will be getting. And apart from that, so we try to use the huge amount of our the carbon materials inside, and doing some of the modifications into that carbon materials. We tried with the dye-sensitive solar cells. So the classically dye-sensitive solar cells will have a TiO2 layer, and then you soak them into the dye, and the dye will be absorbed into the layers, and then you will have a electrolyte inside, and you will have the platinum as a counter electrode. In here, what we did, so we used the tungsten oxide with a carbon into it, and then we try to use as a buffer layer in here. So the idea is, so if this will be working, and then definitely it will work for the perovskite solar cells, because the perovskite solar cell is one way or the other modified from the dye sensitized solar cells as well actually. Right, so that's what we did. And then these are all the some of the um, spectroscopical images you can see. And from that, so we got a very good efficiency, like 10.5 or 10.6 we got, and nowadays we are getting like about 15 to 17% efficiency will be getting actually. So this is kind of, we just used tungsten oxide and into the graphene or the carbon layers. It's a mixed carbon layer actually. So we try to use that one, and then increase the conductivity by having the tungsten oxide inside, and change the electronics of these um, the band gap of these materials, and trying to achieve the quickest possible transfer of the electrons and holes between. And we got a very good efficiency increase, as well as the stability increase as well actually. So, and then this paper was published in the scientific reports. After that, we did a very controlled kind of a study. So in here we just add the weight percentage of the tungsten oxide. We haven't checked these ones, and we thought it's a very good kind of a way forward for the perovskite solar cells achieved in the room temperature. And then we used a very controlled atmosphere or the controlled experimentations, so having different types of variations in the tungsten oxide, and what will be the efficiency limitations of that we have studied. That's in the other paper. So the perovskite as a dye-sensitized solar cells is an another kind of an aspect to look at it. So the classically, if you're using the TiO2 nanoparticles less than 20 nanometer powders, so you will get a very good kind of a conversion efficiency. So your the stability will be good. All these ones will be there. But if you are trying to use mixed perovskites for the dye-sensitized solar cells, and what type of effects it can create, and then whether it can be transferred from these dye-sensitized solar cells to the perovskite type solar cells. That's our aim to do that work actually. So this is a theoretical work, completely theoretically. We try to establish that work, and it worked, but the efficiency was not very great. So you can see the efficiency of the system cannot be more than 3-4% efficiency. So instead, what we did, we tried to establish the fully carbon printed type solar cells. We changed the carbon layers into using the different types of carbons, like a reduced graphene oxide, single wall carbon nanotubes, graphene quantum dots, and then so we use C60, PMMA, all the carbon block. So this is like a type of solar cell. So very steady ones, so completely carbon based ones. By changing these the band gap of these ones by using the different types of carbons, and what type of efficiency we can get. So that's what we have studied. The idea behind it actually, so we try to use these materials into the perovskite in the later stages, and trying to establish a very good efficiency and stability in the room temperature. That's what we try to do. As I explained before, the so I will explain this one, and then we will go back to the previous the slides what we were discussing. So the P25, which is you will get from the market, so that average particle size will be 20-25 nanometers. So this is how it will occupy. It will have the high storage space it will take, and then when you are using the 25 nanometer powders, and your the dye intake will be very, very low. So we try to modify those TiO2 powders, or we synthesize the powders using the CTAP and DTAP and SOS actually. So from that one we try to modify these devices, and we get some of the efficiency improvement. So why do we need these modifications? We try to use these materials in our perovskite as a scaffolding layers as well actually. Right, so that's the idea, because these powders can withstand for the temperature in the longer time. So, and then we used some of these modifications as well for the dye sensitized solar cells as well. So the as I explained in the ambient type perovskite, so I explained to you, so we have used different types of tungsten oxide into it actually. So, and then we try to see what type of efficiency improvement we got, something like that we have established, right? So this is what we try to establish in our lab at the moment, and we try to do the evaporation techniques as well. So we have the machines for that, and so maybe you will see very quickly from us actually. Okay, so this is kind of one side of things. So the other side, so when you are trying to establish the bigger devices from the laboratory scale to the commercial scale activities. So when you have a 0.25 centimeter squared cells, if you get like 15 to 20% efficiency, when you are creating 1 centimeter by 1 centimeter, or 1 meter by 1 meter, so significantly you lose all the efficiency there. So for the 1 meter by 1 meter, you may get 2% or 3% efficiency. So you use huge amount of material, but you get very less amount of efficiency there actually. trying to establish a model or trying to address this one in a different kind of a perspective, like using the concentrated solar cells, and so use the similar devices what we get for 15 to 17% efficiency devices, and then combine them with the concentrated device, and trying to see what type of an efficiency increase we will get. So there are you maybe know, so when you are using the different types of irradiation conditions, like the countries like India, we don't suffer with the irradiation limitations actually. So but in these countries like UK and Europe and some the northern part of the countries, so they get very minimum kind of a sunlight most of the year. So they get like 700, 800. So those type of conditions are most of the time, so you will get less, and then in the summer you will get a slightly better kind of efficiency. So when you are getting these type of irradiations, so what you will do, you will try to get the maximum out of it. So you'll have a lens, and so in the childhood days we try to have the focusing lenses, right, and then to burn the paper, something like that. The similar kind of an idea for the concentrating type solar cells, and try to concentrate the sunlight into a very small area of the device. Instead of paper, you will have the devices here. The device can um, go through quite large amount of heat stress. So when you are putting them in a different types of elements, so then you will have a huge amount of temperature variation from 30 degree to it can go up to 60, 70 degree within a minute time actually, right? So that we try to see so how much efficiency increment we will get, and then what type of an efficiency stability we can get from the PSC. You know, so we call this one as a compound parabolic concentrators actually, CCPC. So these ones, like, so they can just after 10 minutes, 20 minutes, so they will be stabilized in terms of efficiency. But off but the temperature side, so will be huge amount of stress it can go through actually. So that can be managed by some of the elements what we are trying to do. So there is one paper published now actually, so what type of temperature changes can stimulate some of the degradation effect in the solar cells, especially on the perovskite type solar cells there. And as I showed you, so we tried to establish the mixed perovskite, but the efficiency was not very good. So now we try to shift that one from the inorganic perovskites to the organic and inorganic mixed perovskites. So whatever we are using at the moment, we try to establish an kind of a mixture. So how these can be used and what type of a mixture can give you a maximum efficiency. So that's what we try to establish here. So you will see a paper in the physical review very quickly. So maybe in a couple of a week's time you will see that paper coming actually. So this one, as far as we know, so we got the bottom of it actually. So and then we try to establish what the FAB and MAPI structures and how it can be get the maximum efficiency there. Okay, so that's the theoretical work. So experimentally, nobody has done so far. People are trying to achieve it, but they haven't achieved a huge amount of efficiency increment. So in the first couple of slides I have shown you, so we try to use the heat and then trying to establish some of the devices for betterment of the agri-tech stuffs. So in most of the world, these cows or the dairy cows, they will go through a huge amount of heat stress. So they when they are the temperature increases more than 40 45 degree, so these cows will be getting dehydrated and they drink more water and not eating the food properly, and they give less amount of milk actually. So that will be a problem for the community actually. So as most of the entire world will be using huge amount of dairy products actually in their food system. So in India, so this will be increasing day by day, and India also going through these type of heat stress problems. So what we did actually, so we established a system coated with the graphene oxide, and having a device attached to this one can able to absorb the light and keep the having a um, phase change material backside of these devices, and then that can absorb the heat and keep that heat within that phase change material and keep the indoor cool actually. So this we had a prototype and we have tested it in different types of temperatures. The preliminary results published in the scientific reports last year, and we can have a look at those papers actually. So they are very much interest to most of you actually. Okay, so last but not least, actually, I wanted to talk about these ones. So most of the time, we get ideas or breakthroughs from the nature. So the nature is the best kind of a teacher, so because it evolved millions of years. So we just came like 1 lakh or 2 lakh years before to this earth. So before that this earth was there. There's a huge amount of changes that happened actually. So as far as most of the people can agree with me. So the nature can able to establish a system better than us actually, right? The better than the humankind. So these butterflies, what you are seeing here, so they are, we call them as a white butterflies, or the beard butterflies actually here. So these butterflies, so in the winter time, so they need to fly quickly from their rest place, so to save themselves from their so the enemies actually, right? So are the prey. So what they will do, they try to keep their wings like a V shape and try to concentrate the sunlight so into their body, get the body warmed up very quickly in the morning time. So usually the sun will come around 8:30 in the morning here in the winter time. So at that time, so when the low light conditions, so they can able to heat up their body and then get more energy and then trying to fly off quickly. So the theory based on this one, so they have this is the body of the butterfly. The light can come inside and then it can go and totally internally reflected inside and then get the maximum heat into the body and not the light into the body actually. So the what the concentrators will do, so it can get the light and then get the maximize the light here, not the heat. The heat can be dissipated inside the devices. So this is the one we have taken, and we try to see whether are they really doing the basking, or the trying to get the concentrated light into their body. And so we did quite large amount of studies and take the butterflies and establish the system, what type of heat dissipation can happen in terms of reflections, and what maybe the quantum efficiency they can able to generate from those type of lights. And so all those studies we have done. This paper is also in the scientific reports. You can have a look at it actually. So and then what we did, we take the butterfly wings and the original wings of those butterflies. I never killed and nobody killed actually. So whatever our the zoology labs they have, so we have taken some of the butterfly wings and then we try to use them in the devices. So this is our device, and we try to manage so between 0 degree to 100 degree actually. So like exactly talking like 95 degree. We change the angles of these devices and try to see about 20 or 18 degree, so they can able to get the maximum temperature out of these things. So that can give them like an 17 degree, so they can able to get the maximum temperature. So it can go up to 64 degree, from few degree to 64 degree. You can go very very quickly, just like less than 5 minutes or less than 3 minutes, they can able to go. So that's what we have established actually. So now the challenge is, so when you are put the solar cells here, and what type of changes it can create. So as we expected, so they worked better reflectors than the one which is available, which we have like 95% of the reflectance we will get from some of the materials we use for the concentrators here. So the current density was increased 40 percentage, and then the open circuit voltage increased 1.5 times percentage, and then the power increased like 42.3 percentage increase we got actually from the cells. So these are all the silicon based devices we have used. And then when you are taking the butterfly wings, so they are very lightweight, right? So they are extremely lightweight ones. So when we got, so they are 17 times lighter type of concentrators you can get from these type of wings actually, and the better performance, and then better kind of efficiency ratio also you can able to get from these ones. Now the challenge is how to reproduce them. So you cannot kill all the butterflies to use them for the concentrators, right? So you need to create a way forward for these ones. So then we take the SEM figures of these butterfly wings, and this is how it looks like. So these some the beads you can see, so they are in the kind of a nerve system, or maybe a the stem systems what they have in their butterfly wings. They are not properly arranged actually. So according to the butterfly, or according to the nature, they are proper, but according to our perspective, they are not the properly organized ones actually. So creating this one into the laboratory, in the laboratory, will be a big challenge. So we are giving it a go nowadays actually. So we take some of the carbon meshes and trying to have the TaO2 particles in there, and create the lightweight kind of butterfly wings type things. So that's the breakthrough we try to establish from our lab. And using them for the perovskite solar cells as well. These are all some of the papers you may be interested to look at it actually. So this work has been done by many different people in my group, especially so whatever I have used here, done by Dr. Prabhu, Dr. Linshu, Dr. Anurag Rai. So they're all postdocs, and Subran Subandari, so he's the PhD student in my lab actually. So thank you very much for listening, and if you maybe a last message we can say actually, right? So this we have only one earth, so there is no second earth to us. And so the maximum lifetime of a human being will be, you can say, like 70-75 years, right? So you're not going to live in this world forever. So we will be given one earth to handle. And then so it's not only to us actually. So if you calculate the human population and the insect population in the world, so insect population is much higher than the human population actually. The bacteria, viruses, they are a huge amount in the air. So because we wanted to live a comfortable life, we cannot destroy this world, and we have to give this world to and then clean it and keep it safe, and give it to the coming generations, because you are not going to live forever in this world. Okay, thank you very much. If you can do little bit of towards the climate change, and a little bit concern when you are taking the bike to your quite large number of times. If you think about it, do I need to take the bike? And then that's how you can able to bring the change actually there. Thank you very much. If you have any questions, I'm very happy to answer.
Participants, if you're having any questions, you can raise the questions now.
I'll stop sharing.
Good evening, sir. I'm Dr. Ramarao. Will the reflections affect the life and performance of cell, sir? Solar cell.
Sorry, sir, I didn't hear you.
Reflections.
Yes, reflection will affect the solar cell quite a large amount actually. So that's why most of the solar panels nowadays they will come with different types of patterns on top of them. Actually, as you know, so we can't see them by our eyes, but there will be a just kind of sawtooth wave kind of things to reduce the reflection from the cells. Because most of these devices, if you take in the commercial level, the silicon, it can absorb the light from 900 nanometers to 1200 nanometers actually. Some of the thin films can start from 600 nanometer to, it can go up to 1100 nanometers. So that's how, the reflection also will work. So you will get like 40-50% reflection in some cases, but most of the commercially available ones are reduced reflections they will have. So the glass plates will have the coatings which can able to withstand with these reflections.
Yeah, thank you, sir.
Thank you.
Sir, how about the indoor solar cell, sir? Like the third generation solar cell is more suitable for indoor also. How about your point of view, sir?
Yeah, so there are two different aspects to it actually. So, for example, dye-sensor solar cells, perovskite solar cells, organic type solar cells, you can just use them within the buildings as well, like a wallpaper or the wall hangings, or like decorative elements into the building. But how much energy they can able to generate? So that's a big question. So as the house. So 4 or 5 people living house in India or in UK, so you need at least 1.5 kilowatt to 5 kilowatt energy, depends on how you are trying to use. So these elements, so the when you are using indoor stuffs, I don't know whether it can able to generate great amount of efficiency, but you can able to use that. But there are different aspects to it, or the niche people are trying to look at it, like the mobile phones and the gadgets, like a laptop, iPads, or the tablets people are trying to use. So there people trying to use in these type of solar cells, like a combination of these ones. So they can able to generate electricity within the room, as well as they can able to they integrated within the like Dyson solar cells, with some LEDs. The Apple have a pattern for it actually. So they have like LEDs will be glowed first, and then these LEDs can able to give enough light to these solar cells. Then your iPhone will have a phone without a battery, so you can able to go with these type of solar cells. But there are lots of people will be using as a flexible type ones, like if they are going somewhere and just they take it and then using it wherever they want. So those type of applications also they are using. But the commercially, but it needs huge amount of research into it, and then it can take quite large amount of time to come in actually. So, just to add some more point. So any product, if you make, so without having a commercial aspect to it, so that may be a research product, but it will not be the product for the people to use actually in the long term.
It's like we are expecting to that research product into the commercial, those kind of products. Like in the current scenario, IoT devices, sensors, other things are there. It's coming like with the
Yeah.
self-energy harvesting devices, maybe.
Yeah, you're right, actually. Yeah, you're right. Maybe in the future it may come, but I see a very less portion will be there actually, because even in the IoT products like some are necessary. For example, if you are detecting the carbon monoxide in the building, or carbon dioxide in the building, and then trying to control your lighting, heating, air conditioning, all these ones using your the carbon dioxide sensors, actually that's a good way of doing it. But creating the energy within the building is completely a different kind of an aspect to it, actually. But maybe we can see the products in the longer term, maybe in 10-15 years time, who knows. I never thought 10 years before, when I was in Korea, I never thought we are going to call to the people like this, actually. So I'm sitting in my office, and then I'm just talking to about 50, 60 odd people, actually. So that's in India and all around the world. So that I never thought this will happen, actually, right? So but this happened in 10 years time. So who knows, it might happen also.
Yes, sir. Yes, sir. We are also expecting that. Any other questions from the participants? Like you can type your questions in the chat box, or you can unmute yourself also. Like you are having the privilege to unmute yourself. Unmute and you can ask your questions.
Yeah, so if you don't have a question now, but maybe later on, if you have a question, you feel free to drop an email to me. I'll try to answer you as well. Thank you.
Yeah, yes, sir. Yes, sir. Yes, sir. Fine. Like if no more queries, like which one more questions came, sir? Like which will be the best color for the panel, sir? Like
Okay.
three.
Brown color.
Yeah, like a brown color. Yeah, fine, sir. Fine, fine.
Okay.
Yeah, like any other questions? Shall we conclude?
Okay, thank you.
Why?
Uh,
What is the reason behind that? Why the brown color is?
Oh, brown color. You want the answer for it. Okay. So so if you take the brown color absorb near to 550 to 650. So that's the maximum color you will get, actually. So and it can easily blend into the buildings most of the time, right? So and it will not distract the many other species. For example, in here we have some solar farms. So those farms, lots of insects can come and hit the solar panels. So they think it's a water body, so there is a water inside, actually, so they can just go and sit there, actually. So but that's not the case. But brown color can able to give a kind of a pleasing stuffs to the some of these insects as well. And the main reason is the absorption ability will be very, very high compared to the other type solar cells. Like if you take the cadmium telluride, so it will be brown color. So if you can tune the silicon to brown color, like in the amorphous silicon, so it can go up to 16-17% efficiency very easily.
So, in addition to that elaboration, like asking, like why not the black color? Is there any reason, like if any damages?
Okay. Black color, the when you are trying to absorb the entire spectrum, so you will be inviting quite large amount of difficulties as well. So it's not like so you will have the black color, you can absorb all the light, so you will get the maximum efficiency. It's not like that, actually. So when you have the more photons coming inside, so you'll be generating more electrons inside your solar panel. And then the generating an electron is an separate kind of an entity, and then you will be taking that electron successfully from your solar cell. So that is most important than the generating the electrons inside. So most of your solar cells, you take any solar cell, their quantum efficiency converting the light photons into the electrons will be very high, like 80%, 90% will be there. But when it comes to the real type of electrical efficiency of those ones will be dropped down to 20% or less than 20%. Rest of the 60-70% of these electrons will be recombine each other, or it can just you can't able to take them out actually. So that is the problem in the black color modules as well.
Yeah, sometimes maybe the heat also maybe produced, then it will affect the efficiency.
Yeah.
Is that right, sir? Thank you, sir.
Yeah.
Thank you. Like, is there any other examples like butterfly with the we can
So you know the
nature attracted things like
yeah. So
butterfly.
there are quite large amount of things to try. So there, you know for the concentrators, the bees, so they will have a compound lenses in their eyes. So it's not a one lens like us. We will have a one lens in our eyes. So the insects will have a compound eyes, so compound lenses in there. So they can able to see 360 degrees. So that's why if you can have this one, and then they can see full variation of these things. So that type of lenses can be brought into the concentrators as well. That's
Yes,
one
sir.
example,
Yeah,
but there are
thank you, sir.
huge amount. If we can just look at the nature and try to establish something, we can able to get huge amount of lesson from them.
Yes, sir. Like these are all the questions from Keshav and Ajay Sankar, sir. Yeah.
Okay, thank you, Ajay. Thank you, Keshav.
Ma'am, yeah, it's no more questions. Then we can conclude the sessions. Thank you, sir.
Thank you.
Prasanna, ma'am.
So one more question has been posted in the chat box, sir. Is there any method to increase the efficiency for perovskite the solar cells?
Well, there are many different methods actually. So there is a device called tandem structures. So you will take the, I just say one, and then you can just search for increasing the efficiency. They will get plenty. So as I said in my presentation, every 1 hour there is a paper published on the perovskite. So every aspect of the perovskite is covered, most of the research stuffs. The tandem structures, you can take the silicon and perovskite and put them together like different type of combinations. You can able to increase the efficiency from 25 to 27, 28, something like that actually, right? So those type of things also you can try, and people are expecting these tandem devices can break the efficient 30% efficiency mark without having the concentration. There is no cells available above 30% efficiency for the without concentration. So those type of things can be happen in the near future. That's one way to do it, and there are plenty of things to do in the perovskite. Thank you very much. I think we can conclude now.
Yeah. Thank you, sir. Thank you very much for sharing your knowledge and briefing your research work to all of us. And it is highly motivating us towards the research, sir, as you have thrown light on the various paths where we can work on this photovoltaic cells. So thank you, sir. Thank you for being with us.
Thank you very much. Thank you. Good luck to all the participants for the rest of the program. Thank you, Professor Arun Mehta, for contacting me, and then excellent kind of arrangements you've made. Thank you very much. Bye.
Yeah, bye, sir. Thank you, sir. Thank you so much.
Bye.
Yeah, thanks for.
Bye. Talk to you later. Bye.
See you, sir. See you, sir. I'll mail you, sir. Okay, participants. Tomorrow we are having the 9 o'clock session. We started with yoga on stress management. We request all your presence on that. Like we will start by 9. Immediate to that, yoga on stress management. We are having the session with Chetan Solanki sir from IIT Bombay. So thank you all. Just fill the feedback forms. If you have any queries, you can chat me in the WhatsApp group. We will be answerable there. Thank you, one and all. Thanks for your patient listening. Thank you. Thank you so much.
Yes, thank you, sir.